then, what is the 6 and the 7? Yeah. It's the mass number, which is what? Protons plus neutrons. So essentially we say that a proton, a single proton, has a mass of 1. And a neutron also has a mass of 1. Electrons have so little mass that we ignore them. So the mass of the entire atom is protons plus neutrons, to give you the mass number. So looking at that, how many neutrons does that atom have? 3. How do you know? Just subtract it. This number is protons plus neutrons, and that's how many protons there are. So the difference between them must be how many of these neutrons there are. Okay? And the difference between that and that is that they are isotopes. They're both lithium. Because they each have 3 protons, they're both lithium. But because they have different mass numbers, that means they must have different numbers of neutrons. And atoms of the same element that have different numbers of neutrons are isotopes. We're going to move on from neutral atoms to ions. The sodium that we eat, when you look at a nutrition label and it tells you how much sodium is in there, is not in the form of a neutral sodium atom. In vast majority of cases, they are sodium ions. A sodium ion has a charge. So a neutral atom has no charge. An ion has a charge. A sodium ion has a net positive 1 charge. We write that with sodium, the Na, and then we put a little superscript positive. That means that there's a positive charge on that ion. Because protons are positive, electrons are negative. When you have an imbalance of those two things, you have a net charge. So when we look at this, sodium has a positive 1 charge. That tells us that there's 1 less electron than there are protons. That means that there is 1 extra proton compared to the electrons. We know it's sodium though. And sodium always has 11 protons. So if we started with 11 protons and 11 electrons, but we now have 1 more proton than electron, what had to have happened? Because there's 2 options. We can either gain a proton or lose an electron. Which one had to have happened here? So we can eliminate one of them. It had to have lost an electron. Why?
Because it's got a positive charge.
It's got a positive charge, but if we gained a proton, that would have caused the same issue. Why could we not have possibly gained a proton? Yeah. It's simpler than that. We have Na plus. If it is Na, how many protons does it have?
Is it because there's a set number there?
11. If it gained a proton, it wouldn't be sodium anymore. It'd be magnesium.
Oh.
So because it is still sodium, that means the protons did not change. But if we now have an imbalance, something had to have changed. But protons cannot change. So the electrons had to have changed. And because we know we have more protons than electrons, that means we must have lost an electron. If we had gained an electron, what would our charge be? Negative. Remember, electrons have a negative charge, protons have a positive charge. Normally there's one proton for every electron. And so they cancel each other out. And so there's no charge. But once you gain or lose an electron, all of a sudden that balance is gone. And so if you gained an electron, you have extra negatives. And so your overall charge will be negative. If you lose an electron, all of a sudden you don't have enough negatives. And so the positives win out, and you have a positive charge. So here is our sodium ion. How many protons does it have? 11. Because it is sodium, it has 11 protons. That will never change. How many electrons does it have? 10. How do you know? It's positively charged. It has one less. So there are a couple ways of looking at this. Both ways will get you to the same endpoint. Okay? You can think of it just mathematically and say there are 11 protons, and I know that I have one more proton than I have electrons, so I must have 10 electrons. Okay? That works. The way my mind works it is I say, well, the atomic number is 11, so I started with 11 protons, which means I also started with 11 electrons. If I have a positive 1 charge, I must have lost 1. If I started at 11 and I lost 1, I'm at 10. So you can think of it just in terms of electrons, or you can compare the protons to electrons to figure out where you have to be.
Does every element have the same number of protons and electrons?
So, in a neutral atom, if we just pick a manganese atom, it will have 25 protons and 25 electrons. So when you start out, just off of here, they have the same number of protons as electrons. Once you make an ion out of them, then the electrons change. So this is what we're saying. An ion, it's an atom. It's just a changed atom. It's an atom that has gained or lost electrons so that there's an imbalance of the two. That means that we have a net charge. We have two types of ions. Sodium is what we call a cation. It's positively charged. If your ion is positively charged, it's called a cation. If you are negatively charged, it is an anion. Okay? I don't have a good way of remembering these, other than if you're into electrical engineering or wiring, something like that, the anode is the negative terminal. Anode, anion, that's negative. Okay? If this helps, use it. If it doesn't, forget I even put it up there. People tend to like it though.
Do you like cats?
I have a cat, but there's no chemistry dog. There's no chemistry chinchilla or anything like that. And so I have to go with, I either have to make my own meme, which I'm not going to do, or I have to use what's already out there. So this is chemistry cat. There's actually, throughout the semester, I think two times, we'll have a competition in class. And the winner gets to claim the chemistry cat trophy, which one of my students actually made a trophy that looks like chemistry cat. And so you get to write your name in the logbook saying that you won chemistry cat. You will. So this is what really happens on the molecular scale when you make an ion. So this is magnesium. When we start out, magnesium is number 12. So we have 12 protons in the nucleus and 12 electrons on the outside. In this case, we also happen to have 12 neutrons. But neutrons will do nothing. The neutrons have no impact whatsoever on what's happening. What's important is that we have 12 neutrons in the nucleus and then 12 electrons on the outside. Magnesium is here. We'll learn to predict what happens, but what we see here is that we went from 12 electrons to 10 electrons. We lost 2. And if you lose 2 electrons, what's going to happen to your charge, do you think? It's going to become positive, because now all of a sudden we have extra positive. We lost some of our negatives. How positive is it going to be? 2. The charge changes by 1 for every electron that changes. If you lose an electron, the charge goes positive. You lose the first electron, you become positive 1. You lose the second electron, you become positive 2. So we have magnesium atom. Here we have the magnesium magnesium ion, which is a cation. and we write it as magnesium 2+. Yeah.
So if it just has a plus, like the Na plus, it
Yes.
means it's just one?
The plus by itself means an implied 1. In a lot of cases here, you'll see we don't write 1s when they're there. Like the subscript, if you're writing a chemical formula, NaCl is actually Na1Cl1. We just don't write the 1s. Technically, based on convention, we write Mg2+. Sometimes I will say 2 plus 2. Sometimes you will say +2. Sometimes you will write +2. 2+ is the technically correct way to do it. I will never mark you wrong for putting +2 though. I may circle it just to point out that it's not correct, but I'll never mark you wrong and take away points for putting +2. So this is going the other direction. Nitrogen likes to gain electrons. Nitrogen is number 7. So we started with 7 protons and 7 electrons. We gained 3. If you gain 3 electrons, each one of them comes with a negative. And so we now have 3 extra negatives. And so we have an N3- anion. So this is our sodium that we already did. How many protons did we say sodium had? Sodium ion? 11.
How are we going to know whether it's positive or negative charged?
Starting from here, or once things have already changed?
Starting from the beginning.
You'll know in about half an hour.
Okay. Okay.
It's probably, I'm guessing it's the slides just after this.
Okay.
So, sodium ion had 11 protons. How many electrons does a sodium ion have? 10. We started at 11, we lost 1, so now we have 10. This is a chlorine ion. Chlorine is here. How many protons does it have? 17. How many electrons does this ion have? 18. It started at 17. Because it's negative, that means we gained 1. 17 plus 1 is 18. This is oxygen. Oxygen is here. How many protons does that ion have? 8. How many electrons does it have? 10. We started at 8. We have a 2 negative charge, which means we gained 2. 8 plus 2 gives us 10. This is aluminum. Aluminum is here. How many protons does that have? 13. Yeah, 13 protons. How many electrons does it have? 10. We started at 13. We're plus 3, or 3 plus, which means we had to have lost 3. 13 minus 3 is 10. Everybody following this? So now we're going to go the other way. We were looking at symbols, trying to figure out how many protons and electrons there are. Now we're going to go the other way. So the first one tells us to write the symbol for an ion that has 20 protons and 18 electrons. First thing we have to do is figure out what element it is. What element is number 1? It is calcium. There's 20 protons, so we're just looking for number 20. Number 20 is calcium. Can we write the number of protons there? Now, we've got 18 electrons. What is the charge on this calcium? Positive. Positive what? 1, 2, 3, 2. We have 2 extra of these compared to those. And these have positive charges, and so we are 2+. If you want to write that 20 there, you'll never be wrong doing it, but in most cases, we leave it off. The second one, we have 16 protons. What element is that? Sulfur. Number 16 is sulfur. So we have sulfur. What is the charge? 2 negative. We have 2 extra electrons. So each one has 1 negative. There's 2 of them. So we have 2 negative. What about the third one? What element is that? Iron. Iron is Fe. And what's the charge? 3 plus. We have 3 extra protons. And so it's 3 plus. So we're talking about a mass number. And it kind of seems weird probably, because we said a proton has a mass of 1. And I think in the video we talked about it's 1 atomic mass unit, or AMU. That is a completely made up unit. When we're talking about AMUs, when we're talking about the mass number of an atom, those numbers have no connection to real life. All those numbers allow us to do is to compare the mass of one atom versus another. So a carbon-12 atom, carbon-12 has a mass number of 12, is just 12 times heavier than a hydrogen-1 atom. That doesn't tell us how heavy they actually are. There is no scale that measures atomic mass units. All it allows us to do is say that that is 12 times heavier than that. Where these AMUs came from is somebody said, well, let me find the mass of carbon. And they said, well, carbon has 6 protons. If I have carbon-12, there's also 6 neutrons. So let me say, since there's 12 total, that it's carbon-12, and 1/12 of that is the mass of a proton. It's kind of wacky, and we don't have to deal with it too much, luckily. Pretty much the only time we deal with atomic mass units is today. After that, we get into grams and other mass units that have a connection to real life. Basically, what you need to know is that protons and neutrons have a mass of 1 atomic mass unit each. If you remember that, you'll be fine. We can take atomic mass and we can calculate relative atomic mass. If we look at the periodic table, these red numbers at the bottom here are the masses of those elements. But if protons have a mass of 1, and neutrons have a mass of 1, and we completely ignore electrons, the mass of an element should be a whole number. There is no reason for it to not be a whole number. Because you can't have half a proton, you can't have 3/4 of a neutron. You have to have a whole number for your mass number. So why are these not whole numbers? It's because different elements have a number of isotopes. Carbon has carbon-12, but there's also carbon-13, and there's also carbon-14. And so the number up here is the average mass of all of them. Some of them are 12, some are 13, some are 14. When you take all of the carbon atoms in the entire universe and find the average, you get 12.01. And the fact that that number is very, very, very close to 12 tells us that the vast majority of carbon atoms are 12. When you calculated the average, the other 13s and the 14s basically got eliminated. They had a little impact. It's now 12.01, but it didn't change very much. So this is what we call the relative atomic mass. It tells us the average mass of all of the isotopes of an element combined. And we take into account how common each isotope is. So if there's an isotope that is much, much more common, like carbon-12, it gets much more weight when we calculate the relative atomic mass. So this is silver. The relative atomic mass of silver is 107.9. This tells us that there are two isotopes of silver. Silver 107, silver 109. Which one is more abundant? Which one is there more of in the universe?
Apparently 107.
Apparently 107. Why?
Because it's 107. It's not 108, 109.
Right. So she's looking at this number and saying the average is closer to 107 than it is to 109. That number will be closer to the one that is most abundant. It'll be closer to the one that gets the most weight. And so by looking at that, we can tell that silver 107 is most abundant. That is the formula for relative atomic mass. When you write it in that form, it looks ugly. Okay? I know. This is actually very easy. Okay? If we look at it, what it says is relative atomic mass equals the mass of isotope 1 times the relative abundance of isotope 1. You take that plus the mass of isotope 2 times its abundance. And then you add, if you have a third isotope, you add that one, then another one for 4. Okay? So as an example, you'll see how easy this is. We have an unknown element that we discovered on another planet. Okay? There are two isotopes of this new element. The symbols are here. Okay? We have a mass number of 22 and a mass number of 20. And we're given the mass of each isotope. This isotope weighs that much. This isotope weighs that much. And the abundance is given to us also. This means that 75%, or 3/4, of all isotopes of this element are the 22 type. And 25%, a quarter, are the 20. So the question is asking us to calculate the relative atomic mass.
You're going to add them together and divide by 2?
We have to do a little bit more than that. We go back to the formula at the top. We're going to write it in a more manageable form here. So, the relative atomic mass. I'm going to abbreviate it RAM, but that's not actual acronym. You write that on anything else, no one will know what you're talking about. Relative atomic mass equals the mass of isotope 1 times its relative abundance. What is the mass of isotope number 1 here? We'll say number 1 is this one. 21.999. 21.995. And what is its natural abundance?
75%.
75%. Be careful when you put this in your calculator. Unless you have a calculator that will let you do percents, you're not going to put in 75. What are you actually going to put into your calculator? 0.75. So what we have here is the first part. Mass of isotope 1 times its abundance. And right underneath, we're going to do isotope 2. Its mass is 19.996, and it has abundance of 25%. So what we're going to do is we're just going to add that to that. My suggestion on how to do that is to just calculate that. So can somebody do that for me?
16.49625.
16.49625. And then we do the bottom. 4.999. Okay. So we calculated that. We calculated that. And then we just add them together.
So you
my suggestion is to always wait to the very end to do sig figs.
We got 21.49525.
49525.
525.
Okay. And then what are these units here? AMUs. These two masses had a unit of AMU, so what we calculated also has a unit of AMU. So a relative atomic mass of 21.49525. Sig figs here are a little complicated because we had multiplication and addition. Okay? If you see a question like this on a quiz or an exam, something like that, most likely the next step is going to ask you what element is it. And so what you would do is you would take that and you would look up here and you would find the element that has a mass that's closest to it. In this case, it's a new element, and so the mass isn't actually up there. If you were doing one on an exam, it would very, very closely match when it was up there. So if you did it and you got 20.18, you would know it was neon. And so the actual answer to the question won't even be a number. And so you don't have to worry about sig figs then. The number is just telling you what element to pick up off of there.
Is it always going to tell us what the natural element is?
Yes.
Okay.
It will always tell you, but sometimes you may have to think just a touch. So let's say that was blank. Could you figure out what the abundance of it was? How would you figure it out? It has to be 100% total. That's the key to remember. It has to be 100% total. This one is 75%, so that one must be 25. So it may not always be directly written out for you easily like that, but it will be given to you one way or another. Okay. So we've got our periodic table. We've already used it for a bunch of things. We're going to keep using it for new things as we go. Okay? This is our modern periodic table. It didn't always look like this. Maybe 15 years ago, my grandpa gave me a chemistry book from when he went to college. He went to college in the late 40s, I think, and they only had, even just back then, they only had like 30 elements. That was it. We have a whole lot more than that. But the form hasn't changed since then. The form hasn't changed for a couple hundred years. So as they found the new elements, they knew where to put them. The periodic table in his textbook had missing spots. Like they would know that gold was down here, but they had no idea iridium was a thing. But they knew that gold was going to fit right there. There are patterns up here that tell us where things are going to be. The simplest pattern is just increasing number of protons. So we go 1, 2, 3, 4, 5, 6, 7, and so on. That's the simplest one. Top to bottom, left to right, just like you would read, it goes increasing numbers of protons.
Why are some of them invisible? Is it because they're not yet found?
Invisible as in here?
No, down below. Yeah.
These?
Yep.
They are, my guess is those are theoretical
So they're not yet found.
elements, or the ones that don't have a two-letter symbol, those are definitely theoretical. If I had to guess, maybe these are ones that people have made in a lab, but are not natural elements. You can force an extra proton into an atom, and all of a sudden you now have a new element. If you started with 92, and then you push a proton as hard as you can to get it to stick, all of a sudden you have 93, you have Neptunian. But it is really unstable. It'll last like a femtosecond, like trillionth of a second. But you get credit for making a new element. And so that's why, yes, they have existed, but they're not.
Thank you.
When we look at the periodic table, we look at rows and we look at columns. And in both cases, what row and column they are in is very important. A column is called a group, and a row is called a period. That's why it's the periodic table of elements, because we have periods and the elements are going to change in a recurring pattern as you go from left to right in a period. So if you look at potassium, and then you go calcium, and scandium, and titanium, and vanadium, the properties of those elements are going to change. But when you get back down here, rubidium is very much like potassium. And then as you go to the right from there, the change in this row is going to be almost identical to the change in this row. So what that means is that the group that you are in is going to determine your properties. When you start on the left and then you go to the right, it doesn't matter what row you're in, your properties change in step with the other rows around you. If you go one step over, you're going to have the same properties as beryllium, which started over here and took one step over. And so groups, the columns, act very much like each other. Barium is very, very similar to beryllium. Germanium is very similar to carbon. Bromine, very similar to chlorine and fluorine. So this is potassium in water. Have you ever heard of putting sodium in water?
Yes.
Yes? What happens? Fire. Fire happens. Yes. Sodium reacts with water to make hydrogen gas, which we've already learned is flammable, and a whole bunch of heat. If you make hydrogen gas, it's flammable and heat, you basically create fire on your own. So sodium is here. Put sodium in water, it'll burn. This is potassium. Potassium is in the same group, in the same column, so you would expect it to behave the same. So potassium, when you put it in water, it burns. Same thing with lithium, and rubidium, and cesium, and francium. Those are all in what we call group 1. If you're in column 1, you're in group 1. And this group has a name. We call them alkali metals. Generally, as you go down, we'll learn why probably 2 months from now, but the why doesn't matter at this point. As you go down in group 1, the reaction with water gets more and more violent. So sodium wouldn't put off as much fire as potassium is here. But as you go down, start adding rubidium and cesium, you put them in there, it's like a bomb going off. As soon as it touches, it just blows up. So, first day of class, we talked about metals and nonmetals. We said that the metals are on the left-hand side, and the nonmetals are on the right-hand side, and that there's a stair step. Essentially, we're going like this. And the things that are on the left of that stair step are metals. The things that are on the right of the stair step are nonmetals. And then the things that are right on the stair step, not diagonal, but the things that are right on it, like silicon and germanium, they are called metalloids. They're similar to metals and nonmetals. They have properties of each, so they're kind of caught in between. They look like a metal, but they react like a nonmetal. So this is what we done earlier. The metals are everything on the left. The metalloids are on the stair step. And then the non-metals are on the right. So we've talked about elements and looking at the periodic table in a couple different ways. We've talked about groups as the columns. We've said the periods are the rows. We have talked about metals, non-metals, and metalloids. One extra classification is these ones in the middle here. They're called transition metals. They are metals. They're definitely metals. They're shiny and they conduct electricity. They are metals in all forms of the word, but they have their own term, transition metals. Okay? So we've got alkali metals are group 1. We've got transition metals are in the middle. And then here, this is telling us the group 2, column 2, starting with beryllium here, are the alkaline earth metals. Second to last column, with fluorine, chlorine, and bromine here, are the halogens. And then the last column are the noble gases. This makes a differentiation between transition metals and inner transition metals. You want to cross off the inner transition metal part, you'll never see that again. It's just the transition metals are this block in the center here.
What about hydrogen?
We'll come back to hydrogen. Hydrogen's weird.
Okay.
So we said alkaline metals are group 1. Alkaline earth metals are group 2. I don't know who decided to make the two names so similar. Okay? Unfortunately, we don't get to change it. If you can come up with a way to remember which one is which, good for you. Okay? My method makes sense in my head, sort of. It's not going to make sense in yours. I think for some reason, I associate calcium with the earth. Okay? I don't know why. Calcium is in this group, and so that group in my head must be the alkaline earth metals. It doesn't make sense, I know. If you can use it, go for it. Otherwise, you're just going to have to memorize it. So we have the alkali metals, group 1, and the alkaline earth metals in group 2. Then we've got the halogens. Halogens are group 17 here, fluorine and everything below it. And then we have the noble gases. Noble gases are the last group, helium, neon, argon, krypton. They're called noble gases because they don't react with anything. They're completely unreactive. And so the name came from noble people and nobility who want nothing to do with silly peasant elements. Okay? They're their own thing. They're as good as it gets. They don't want to react. They can't get better. I'm just going to sit in my castle and do my own thing. Some of the elements exist in molecules, not single atoms. We call them the diatomic elements. And they're diatomic molecules. Diatomic meaning 2 atoms. So we have this L shape. So in this picture, they have hydrogen here. In some periodic tables, you may see hydrogen written both here and here. The vast majority of them will not have hydrogen written there. So you need to remember which elements are diatomic. There's an L shape or a 7 shape, starting with N, goes N, O, F, and down. Okay. Here they stop at iodine, but astatine is also. So essentially you have this 7 shape plus hydrogen. I remember the plus hydrogen. If you want to remember that hydrogen can be written here, then hydrogen is in the same group as the rest of them, And so that would explain why it's diatomic. So you've got that shape plus hydrogen. Those elements will never exist on their own as single atoms. You will never see a single nitrogen atom sitting on its own. Nitrogen ions, yes, but not a neutral atom. If nitrogen is in the form of a neutral atom, it will be two of them. It will be N2. You have N2, O2, H2, F2, Cl2, Br2, and I2. Any other element will exist as single atoms. Sodium, there's one sodium atom here, one over here, one over here. They are not in these molecules. Okay. So when we were looking at the ions before, we said that some of them make positive ions by losing electrons, and some of them make negative ions by gaining them. We need to be able to predict whether an element is going to become positive or negative, and then we need to be able to predict how positive or how negative. Is it positive 1, positive 2, positive 3? If we look at sodium, sodium was one that we already did, and we said that it was positive 1. Everything in the same group as sodium behaves like sodium because they're in the same group. So everything in group 1 will make a positive 1 charge. So any element in group 1, if it forms an ion, will become positive 1. The alkaline earth metals, in group 2, we saw magnesium, it formed a positive 2 charge. Every element in group 2 will form a positive 2 charge. Oxygen and sulfur will make a negative 2. Halogens, negative 1. And then noble gases do nothing. Okay? For the most part, everything in the middle here forms plus 2. There will be just a few exceptions that we'll go over today. But if it's not one of the exceptions, all of the transition metals make plus 2. So we have plus 1, plus 2, minus 1, minus 2, and then this is actually also minus 3. And we'll see why that happens in a few slides. Hopefully that'll help you remember, because then it'll make sense. So, we said that noble gases do not react. And the reason is they say that they are already as good as it gets. They have nowhere to go but down. So they're not going to change. So the reason they are as good as it gets is because they have what we call 8 valence electrons. Every element, when it forms an ion, is going to gain or lose electrons as they need in order to get 8 valence electrons. And they're going to do that by trying to get essentially to the nearest noble gas. So sodium starts with 11 electrons. Neon here is a noble gas, and it starts with 10. If sodium loses just 1 electron, it will then have 10. And that's how many a noble gas has. So that's why sodium loses 1. It wants to go backwards to 10 and be like neon. Metals are on the left-hand side. And so if they want to go to the nearest noble gas, the nearest noble gas is backwards. Sodium is only 1 step away from neon. It is a whole bunch of steps away from argon. If it wanted to be like argon, it would have to gain 7 electrons. It's a whole lot easier for sodium to lose 1 and go backwards to neon than it is to gain 7 and go forward to argon. So because metals are on the left-hand side, it will always be easier for metals to go left. to go backwards to the previous row and be like that noble gas. Nonmetals are on the right-hand side. They're over here, which means that they are closer to the noble gases in their row. They're almost a noble gas already. So it's easier for them to just gain 1 or 2 to get there than to lose 6, 7, or 8 and go backwards. So metals will form a positive charge. Nonmetals will form negative charges, always. If you are a metal, you will form a positive charge. If you're a nonmetal, you'll form a negative charge. Can anybody figure it out?
Oh, it's a metal.
It's a metal cat, yes. And so metals form cations. If it helps you, good. If it doesn't help, please forgive me. So, we've got our sodium. This is a sodium ion. How many electrons does sodium ion have? How many did it start with? 11. How many did it lose? 1. So how many does it have? 10. Magnesium. It started with 12. How many did it lose? 2. How many does it have?
12.
Started with 12. We lost 2.
Oh, so it has 10.
Has 10. Here's aluminum. How many did it start with? 13. How many did it lose? 3. So how many did it have? 10. Here's oxygen. Oxygen started with 8. It gained 2. How many does it have? 10. Fluorine started with 9. It gained 1. It has 10. How many electrons does neon have? 10. They all wanted to be like neon. The metals here, sodium, magnesium, and aluminum, went backwards to neon. Oxygen, fluorine went ahead to neon. Earlier on, we showed nitrogen. Nitrogen started with 7, and in that picture, it gained 3. So nitrogen also got the 10.
Because they all wanted to be like a noble gas?
They all want to be like a noble gas. So this is just giving us an element name. We have to write the symbol of the ion. So beryllium is Be. What's the charge of a beryllium ion going to be just by looking at the periodic table? It's
4.
number 4. What's the charge on the beryllium ion? Positive. Beryllium is a metal, so it's going to form a positive charge. Positive what? 1, 2, 3, 18, 2. It's in group 2. Group 2 forms a 2+ charge. Now we've got aluminum. Aluminum is 8L. Aluminum is here. What charge do you think of that is going to form? Positive. Positive what? 3, actually. We have 13. It wants to be like 10. So it's going to go back 1, 2, 3 spots. So aluminum, 3+. Phosphorus is here. That's a P. What charge do you think phosphorus is going to have? Negative. Negative what? 3. It is 3 spots away from a noble gas. So it starts with 15, it wants to get to 18, it needs 3 more. So it's going to form a -3 charge. Yes?
So it just goes to like the closest noble gas?
Correct. So for metals, the closest one is backwards. For the non-metals, the closest one is forwards. It's like being on a plane and tell you go to the nearest emergency exit, keeping in mind the nearest emergency exit may be behind you. And so this is going the nearest noble gas. Sometimes it's forwards, sometimes it's back.
What if you're in transition? Are you going?
Transition metal is in here. These are metals, and so they will go backwards.
So that's when it starts getting complicated, because you're gonna go back that way, right?
Yes, and the reasoning why they go forward and backwards, we'll start talking more in depth about these electrons. It'll become more clear why these go that way.
Okay.
Yeah.
What about group 14?
Group, good question.
Are they useful?
So group 14, let's just pick carbon as an example. It has 6. If it wants to be like neon, how many does it need to gain? 4. If it wants to be like helium, how many does it need to lose? 4. So really, group 14 can form both positive and negative charges. But it takes more and more energy. It's harder to gain 4 electrons than it is to gain 3. It's harder to gain 3 than it is 2. It is so difficult for carbon and everything below it to gain or lose 4 electrons that it basically never happens. And in this class, it will never happen. Okay? So in this class, group 14 forms no charge whatsoever. You'll never even be asked that. Okay? So we've got +1, +2, +3. For the most part, +2. And then -1, -2, -3. Okay. So in order to understand really on the subatomic level why these things are happening, now we have now 2 non-functioning clocks. Is that one working now?
I think someone switched it.
Oh.
Because that one takes that.
So we have to really understand why the electrons do what they do. Okay? And when they first started learning about electrons a long time ago, they came up with this model. And for most purposes, this model works great. Okay? We are actually going to use this model for a real purpose in lab in a couple weeks. Okay? But nowadays we know it's not actually correct. So Niels Bohr made this model of the atom. Some of you may have made a model of this in middle school or something. Okay? It essentially looks like a solar system with the nucleus in the middle and then electrons going in orbits around it. And so in this model, you have different, what they call shells. A shell is basically an orbit. And you can have so many electrons per orbit, and then you move out to the next one. As you add electrons, you just add shells and orbits on.
And the outer shell is the one that's swapped to become like a noble gas?
The outer shell, we'll learn, is the one that reacts. Electrons that are not on the outer shell are shielded. They're protected from everything around them by the outer shell. So it's only the outer shell that's going to react. And so the outer shell, say you have 1 electron in that outer shell. Most likely that 1 electron is going to get lost. If you have 7, we'll learn, a full shell is 8. And so if you have 7, then you'll gain 1 to get to 8. But we realize that that solar system model isn't actually correct. Electrons don't fly in perfect little circles around a nucleus. They are not in orbits, they are in what we call orbitals. An orbital is just sort of a region of space. Okay? It's not nearly as well defined as an orbit. An orbital is just a place that an electron can be. It can be anywhere in that orbital, but we can never know exactly where it is. An orbital is 3 dimensions. The orbit is just a single 2-dimensional line around the sun in the center. An orbital is 3 dimensions. And so, if you look at an orbital, we draw an orbital as, in this case, a sphere. But in reality, it's a sphere that the electron can be anywhere in. So this picture up here is showing that the electron can be anywhere in that. And so each dot here is a place that the electron can be.
Is that the electron cloud?
This is an electron cloud, yes. because the electrons are just flying around. We never know exactly where an individual electron is, so they just kind of create a cloud. And with the orbitals, we get what we call principal energy levels. It's very similar to adding an orbit on. As we add more electrons, we occasionally have to add a new orbital on the outside. So rather than drawing a bigger circle, think of it as a bigger sphere that goes around the smaller sphere. It's kind of like a nesting doll. If your small sphere gets full, you get a bigger one, put the smaller one inside of it, and now you've got some extra space. That's essentially what happens here. This is called a principal energy level. A principal energy level is an orbital of the same size. Okay? For you, the most important part is to realize the principal energy level is just the rows on the periodic table. So, if we look at magnesium, the outermost principal energy level is 3. That's it. So if you want to know the principal energy level of an element, look at what row it's in. So you don't need to know these shapes, okay? This is just up here to show you that we have different shapes of orbitals. We're going to learn more about these letters, and we're going to use the letters, but we're not going to worry about the three-dimensional shapes. But essentially what you're looking at here is that different orbitals have different numbers of little spots in them. And each spot, let's say it's just 1, here we have 2, and then 4, and then 8. Each spot can hold some electrons. And so as you go from here to here to here to here, an F orbital holds more electrons than a D holds more than a P, and a P holds more than an S. Okay? So we have 4 types of orbitals. S, P, D, and F.
That's the blocks, right?
That's the blocks.
Okay.
We are not going to deal with Fs. Okay? We don't want to get Fs in this class, right? So we're going to ignore them. You need to worry about S, Ps, and Ds. Forget about Fs. Fs are these elements down here, and we're not going to touch them all semester. So this is what she meant by the blocks. What you need to do is you need to get to the point that you can look at the periodic table and immediately know what block an element is in. And by looking at that, you're going to know where the electrons in that atom fall. And so we have the S's. The S's are groups 1 and 2. It's this block over here. We have the D's, which are this block here. And then we have the P's, which are this block here. So we have S's, D's, and P's.
Except for helium.
Except for helium, it's wacky. You'll see why in just a few minutes. But sometimes we write hydrogen here. Sometimes we actually write helium there. So helium actually is an S, but that's not going to come up too often. So you have S's, D's, and P's. We're going to use this to write out where the electrons in an atom fall, where they live. We have a few different ways of writing it out. The first one is called an orbital diagram. In an orbital diagram, we write the symbol for the element, we write some boxes, we label the boxes as what orbital they are, and then we put arrows into the boxes representing the electrons. So this is carbon. We look at carbon. How many electrons does a carbon atom have?
6.
6. So when you write the orbital diagram of carbon, you have to write 6 arrows. So my suggestion is when you start doing this, you know it's carbon, so write a C. You know it has 6 electrons. The number 6 isn't going to be part of your answer, but just write it down for your own reference. So you know when you finish, you have to have 6 arrows. Okay. Then write the boxes. You have to remember S orbital. gets one box. A p orbital gets 3 boxes. A d gets 5. And each box can hold 2 arrows. Okay? Once we start doing them, it's all going to make sense. Okay? But at this point, s orbitals get 1 box, p's get 3, d's get 5. Each box gets 2 electrons. And then these numbers, this is the 1s because it is period 1. So if you look at the periodic table, the 1s orbital is hydrogen and helium. S's get 1 box. Each box holds 2 electrons. So 1s can hold 2 electrons. Hydrogen and helium. Once we move past helium, we're down here. This is still the S's. We're still over here, but we're now in period 2. So this is 2s. That's 3s, 4s, 5s, 6s, 7s. And so if you want to write the orbital diagram for carbon, you always have to start in the top left corner. No matter what element you're doing, you start in the top left corner, and then you work your way to where you need to be. So we're going to start in the top left corner, and then the first orbital is 1s. If this is 1s, what orbital is this?
2s.
2s. Carbon is here. What orbital do you think carbon is in? What period is it in? It's in row 2. So it's 2 S, D, or P? It's P. These are the P's. And so we've got 1s, 2s, 2p. So we wrote 1s, 2s, 2p. The s's got 1 box each. The p got 3 boxes. So now we have one S, 2s, 2p. But if you look at it, it looks like those arrows are put where they are for a reason. They weren't just equally spread out. So we're going to start in the top left corner, and we're going to write 1 arrow for every element we move. And so the first one is hydrogen. It goes there. That's the hydrogen electron.
How do you know it goes up?
We'll get that. The next one is helium. I brought 1 up, 1 down. You can never have 2 arrows in the same box going the same direction. If you want to write the first one down and the second one up, that's okay. But you can't put 2 up, you can't put 2 down. Then we've got 2s. So we've got lithium and beryllium. There's 2 there. That's 4 electrons. Now we've got the 2 p's. We know carbon has 6. We've already used 4. So there has to be 2 left. We can also tell that there are 2 electrons in the 2p because there is 1, 2. It is the second element in the 2p's. So we have 1, 2. We didn't put 1, 2 though. Electrons are antisocial. They will not form pairs unless they have to. Okay? Like when you went in the lab the first week of class, everybody found individual spots until there were already 12 of you in there, and the 13th person came in and had to find the lab partner. Okay? So the first one's going to go there, and the second one's going to go there. If we had a third one, it'd go there. But once that fourth one comes around, it's got to find a partner. So these are the rules that we just followed. The outflow principle tells us that we start with the 1s, then we go with the 2s, and then as you get higher and higher, we go to 3s and 4s and 5s. The Pauli exclusion principle tells us that you can only have 2 electrons per box, and that the arrows have to go different directions. The arrows represent spins. electrons spin like planets. And you can't have two electrons in the same orbital spinning the same direction. They don't like that, and so they'll spin opposite directions, which is why you have to put one up and one down. And then Hund's rule is the one that tells you don't pair them unless you have to. But you cannot move here until you finish that one. So you can't take one of these and put it there.
So why did they have to get paired together? Because they're only allotted one box each?
Right. There are two electrons in one s, but there's only one box.
Okay.
So you fill one s, then you fill two s, and then you fill two p. So let's do some more examples. And this is where you're really going to see how we do this. So we've got hydrogen. Hydrogen is the simplest one there is. Hydrogen is H. How many electrons does it have?
One.
One. What orbital is hydrogen in?
One.
1s. So I have 1s. How many boxes does 1s get? One. Why 1?
It only has one.
It's an S, so it gets one box. You always have to write all of the boxes for that orbital. You notice for carbon here, even though I only used 2 of the ones in the 2 p's, I still wrote the third one. You always have to draw all the boxes, even if you're not going to fill them all. So here's hydrogen. We got our 1s in our box. What do I put in the box? One up arrow. Or down. Normally people put the up first. I don't know why. That's done. So that is the hydrogen orbital diagram. Now we'll do phosphorus. Phosphorus is a little more complicated. Phosphorus is number 15, so we're going to have 15. Now there are really 2 strategies you can take. Okay? You can say phosphorus is here. What orbital is phosphorus in? It's in 3p. If it is in 3p, I know that everything below 3p, everything before 3p is going to be full. Okay? Or you can draw the boxes and say, I have 15, let me start at the beginning, follow the rules as I go, and see where I finish. Okay? So, what is the first orbital? We have to start in the top left corner, always. 1s. 1s is always first. How many boxes does it get? One. What comes after 1s? We fill 1s, now we're here. 2s. How many boxes does it get?
One.
One box. What comes after 2s?
P.
P's. 2p. We've got 2p, and there are 3 boxes in that. What comes after 2p? 3s, which gets 1 box. And what comes after 3s? What is this? 3 what?
P.
P. And this gets how many boxes? 3.
Can you explain that one more time?
Yes. So we start in the top left corner. We're going to work our way through the orbitals until we get to the element we're trying to do. And so we're trying to get the phosphorus here. We start in the top left corner. We start with hydrogen. And hydrogen is here. It's in the S group. It's in the S block, and it is row 1. So there's 1s. The 1s holds 2 electrons. It holds basically the hydrogen and helium electrons. So that's 1s. And then we come down here. This is S still, but it's row 2. So it's 2s. S's get 1 box. It gets 1 box because there are 2 elements here. So there's going to be 2 arrows to represent those 2 elements.
Lithium and beryllium.
Start again.
Lithium and beryllium.
Yes, lithium and beryllium. And then we come over here. There's an empty spot here. So we skip the D's in the middle. Come straight over to the P's. This is row 2, and it's the P's. And so we have 2P. P's get 3 boxes. P's get 3 boxes because there are 6 elements in the P's. If they come in pairs, you're going to need 3 boxes. That's why there are 3 boxes in the P's. So we fill that. Now we come down here, we're in 3. We're back to S. We have 3S, gets 1 box. And then we go 3P. Phosphorus, where we're trying to end, is in 3P. We write the 3P boxes, and then we stop. We don't need to go any orbitals past 3P.
But 3P is going to have one of them, correct?
We'll see.
Okay.
And so, at this point, this is where you can decide what strategy you want. You can say, well, I know phosphorus is in 3P, so everything before that has to be full. You just go through and draw your little arrows, okay? We're going to take the more straightforward approach that doesn't require as much logic, okay? If you follow the rules will get you the right answer. So we need 15 electrons. I'm going to go 1, 2, and then I'm going to move on. I filled the 1s, now I can move to 2s. That's 2, 3, 4. Now I move to 2p. When I go to number 5, I'm going to put it there. And number 6, I'm going to put there. Then 7. And I'll come back to 8, 9, 10, 11, 12, 13, 14, 15. For those of you over there, there's 1 arrow per box. And that's 15, so we're done. A little quicker, if you said, well, I know these are full, I'm going to fill them, and then I know phosphorus is the 1, 2, third one in the P's, so there must be 3 of them there. So in that case, you don't even have to really realize that there are 15. You figure out that there are 3 here, and then when you fill in everything else, it in the end adds up to 15. So, before we move on, we'll do one more example, then we'll take our break. One of the slides I breezed past showed an exception. So we said that this is 3S. This is 3P. So what do you think potassium and calcium are?
4S.
4S. What do you think this is?
4P.
4P. What do you think this is?
4D.
You think it's 4D.
1D.
These are behind one number.
Oh, they're 3D.
These are 3D. People are going to get that wrong on the quiz. People are going to get it wrong on the exam. People are going to get it wrong in the lab. People are going to get it wrong in the final exam. Let it not be you. Okay? When you write the numbers for the D's, they are one number behind. So this is 4S and 4P, but this is 3D. This is 5S, 4D, 5P. Just to overcomplicate things. If you haven't noticed yet, I slam down when I write. So we're going to do an example that includes that. So let's do titanium. It's number 22 there. So I've got titanium. What's the first orbital? 1s always, and then that gets 1 box. So we've got what? 2s gets 1 box. What comes after 2s? 2p, which gets 3 boxes. After 2p, we have 3s, 1 box. Then 3p, this is where we were with phosphorus. Then we go from 3p down to here. What is this?
3D. Oh, 3S.
4s comes, we got 4s. Then we get over here. This is 3d. And these get 5 boxes because there are 10 elements here. So to hold 10 arrows, you need 5 boxes. And so we know that we are in 3D, so everything down here must be full. So I'm going to go through, fill everything. Now, how many electrons, how many arrows are in the 3D? 2. Why 2? It's the second one in. So scandium would have 1, titanium would have 2, vanadium 3, chromium 4, and so on, until you get zinc, which has 10. So titanium has 2. I'm going to put the first one there. Where does the second one go? In the next box. So that's the orbital diagram for titanium. Just don't forget that the D's are one number behind.
So it's 10 boxes?
So 3D gets 5 boxes because there are 10 elements and there's 2 per box.
Wait, why is there 2?
Why are there these 2?
Like for
Right. So you're asking why there are 2 in 3D?
yeah.
Because if we come over here, potassium and calcium were the 4s. Then we get over to the 3Ds, and titanium is the 1, 2. It's the second one in, so it has 2 arrows.
Is also this is 22?
That is a coincidence.
Mm-hmm.
Yeah.
Okay.
And so, if you counted that there are 22, and you followed the rules and started here, and you did 22 following the rules, you would get that.
So it's not, we don't follow those.
It depends on which method you want to use. If you want to use the first one we did for phosphorus, where we said phosphorus has 15, let me start here, follow the rules as they go, and let it end where it's going to end. Okay?
And you have to.
And count as you go. That will always get you the right place. So for titanium, you would do 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, stop.
Mm-hmm.
And you would have the correct answer. The way we did it here is we said titanium is the second one in 3D, so I'm going to put 2 arrows there and fill everything else in behind it.
You have to make sure you have the right blocks up.
Right. Right. So no matter which way you're doing it, you have to write the blocks. It's just a matter of how you want to fill them. There are 2 ways to do it. Yes?
What's the purpose of orbital diagrams?
It's going to tell, it tells us, we'll get there.
Okay.
It tells us why why ions form the way they do. Let's take our break now, and we will start at 37 after on this clock. So 10 minutes. If you have the post-it, I'll take it.
take it anyway.
How come this isn't like in the book anywhere, so that we can like use this one? How hard is
It was made by the department to go with the department final exam. So I use it the entire semester so they can get comfortable with it. But that's not from, there's totals from here and there to make. And so,
Because we're just basically using the internet, because it doesn't tell us in our book, and I think the whole like,
yeah.
the, thing for me, like, the acronym,
I'm not sure I do.
Anyway, it's like, so you remember like all the, like, Hero and,
Oh,
yeah.
yeah. Some professors give it to their students, one not. So because they know, I don't let people keep it. Because they may not want their students to know what it's on. You know what I mean? So I don't want their students getting a copy of it. 'Cause
Does anybody have an iPhone charger?
I'm
Should
sure
be that
some
charging
people-
station downstairs there for
Yeah. This one has some extra information as well, so.
Right.
So what you got is you've got symbol, then the number. I would ignore all of this, but I would ignore this 120 and the 2 plus and 4 plus.
Because this is your atomic number and this is your mass,
Correct.
right?
Correct.
This is gonna be handed out on our tests, but you won't let us keep it now. Like, let us look at it.
You'll have it for the quiz today. You'll have it for quizzes and exams. But I'm not allowed to let you keep it. Those are time configurations or conversions.
See, we're
So-
also going to conversions.
So it has these central prefixes, and then there are conversions, the temperature conversions are on some of the other. This isn't going to help you with the conversion, it will give you the conversion factors.
I'll show you my acronym.
You'll never have to know the conversion factors.
King Henry died Monday, drinking and stuff.
It's more complicated, because you really only need the centi, milli, and kilo. Those are the
But
ones.
this is how you do this responses. So
Right.
that you know
Okay.
back, you know what I mean?
I see.
So that you can get placement right, the decimal placement right.
The way you would use this, say you wanted to go from, well, say meter would be upside down, would be here. This is either positive exponents, there's a positive 1 there that's not included. So it's positive 1, positive 2, positive 3, and negative 1, negative 2, negative 3. And so the split between the positives and the negatives is the split between things that are bigger than each other and things that are smaller than each other. Right. So a line right here
That's my Monday.
would be a meter. And so then a decameter is 10 meters. A meter is 10 to the second, which is 100. Yeah. We'll go over the Canvas one. We'll always go over the Canvas homework for not the Wiley, but you can always ask me questions about the Wiley. We'll go over. this issue is going to be a big problem on this exam. If you don't know how to use them in dimensional analysis, that dimensional analysis is the thing with the boxes, where we can't get the units.
Oh,
We have to get the grid.
yeah. That's when you're converting.
Right. And so what this essentially tells you is what numbers to put in there.
Yeah. That,
We will.
so if you're going from like milliliters to milligrams,
Well, that you would go from liters to milliliters. So if you're going from liters to milliliters, a liter is that line there. So if liter is here, milli is 10 to the negative third. Which you put the 10 to the negative third in your calculator, it will tell you 1.001, which is 1/1000. And so you would divide your number by 1,000. So if you wanted to convert 5 liters into milliliters, you do dimensional analysis. Right. So liters is that the line. So with dimensional analysis, that unit always goes there. And so this is telling you that milliliter is 1/1000 milliliter. So that means that there are 1,000 milliliters in 1 liter. 1 liter is milli is 1,000. So that tells you that there's 1,000 of these in 1 liter. And so 1,000 of these in 1 liter, I got that set up. You 5 times 1,000. So because that unit is there and there, they cancel. So your unit is milliliters. Multiply it. I don't mark you as absent. If you read, you missed the quiz. So, but that's essentially the incentive to nothing.
didn't know you needed my word.
So is the test next Tuesday? When's the first test? Tuesday.
Miss Emma. Brittany. There's no Brittany here, right? There's no Brittany or Emily here? Okay. Then I'm not going crazy. I'm just already crazy.
I wouldn't say that.
It's only been a few weeks. Give it time.
We're the ones that feel crazy.
Okay, so that was the orbital diagram. Okay, that is the most complicated form of it. But that is really cumbersome to do, right? And so we have other ways to write it that are a little more straightforward. The first one is called the orbital diagram. It has the same exact information, but instead of boxes and arrows, we just use letters and numbers. And so this is 1s. There are 2 arrows in it, so it's 1s, 2. 2s, 2, 2p, 2. And you're done. So this is a lot easier to read off the periodic table very quickly. Let's say I want to do germanium. I know that everything before that, before this, which is 4p, is full. So it's going to be 1s2, 2s2, because I know they're 2 because they're full. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. Obviously, you're going to go slower the first time you do it. But it's straightforward. I mean, you're not worrying about how many boxes do I draw and where do I put the arrows? Are they spinning up? Are they spinning down? You're just writing it out. Okay? If you can do the boxes, you can do this. If this doesn't make sense to you, you can always draw the boxes and then figure out what this is. 1s2, 2s2, 2p2. So let's do phosphorus. Phosphorus is here. Where's the first orbital? 1s. How many are in it? 2. So we got 1s2, 2s2, 2p6, 3s2. This is 3p.
3p6.
3.
Oh,
Wait, are
Good.
you counting the boxes or the arrows?
The number represents the arrows. The superscript number. This number represents the arrows. This number represents the row, unless it's D, then it's the number behind. So phosphorus was 1s2, 2s2, 2p6, 3s2, and then we get to 3p, but it's not full.
3p3.
So it's 3, because phosphorus is the 1, 2, third element in the 3p. So it's 3p3. And so sulfur would be 3p4, 3p5, 3p6. Here's manganese. Manganese is here. What's the first orbital? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5. 3d5. If where we were going was past, let's say we were going to germanium, then it'd just be 3d10 and moving on. But because where we were finishing was in 3D, we have to stop and think. How many are in 3D? 1, 2, 3, 4, 5.
I don't remember you start counting and all that, and you're like, oh, well, where is the element?
Yeah, it's tempting to just keep going.
Yeah.
You've done the whole table and you've forgotten stuff. Yeah.
I thought germanium was part of P, because it's under.
Yeah, so I must have confused you. With manganese, we did 3D5. And so the point I was making, I was saying, because we stopped in 3D, we had to stop and think about it's 5. If we were going past 3D, like well, say we're going to germanium, that means we're going to 4P, and so we can just say 3D10 and be done with it. Does that make sense?
Yeah.
So aluminum, we're going here. Read it out to me.
1s2, 2s2, 2p6, 3s2, 3p1.
3P1. This is 3P, 3, and it's in P, and it's the first element in the 3P, so it's 3P1. Scandium. Scandium is here.
So 2s2, or 1s2.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And potassium, let's say, well, I mean, if you did scandium, you can do potassium. Now, bromine, let's just do the bromine. Got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. We go back up to 4. Only the D is behind the number. So we got 4s, 3d, 4p, and it is the 1, 2, 3, 4, 5th element in the 4p. So it's 4p5. Yeah.
So if you ask us to like do the diagram, you can do either the boxes or the shorthand?
It will always be specified for you. So it will always say orbital diagram. Orbital diagram is the one with the boxes, or electron configuration. Okay. And if there's a question that I give you on a quiz, or that I give you on an exam, I will tell you this is the one with the boxes. This is the one without the boxes.
Just like that?
It's very similar to that. The final exam I did not write though. So on that one, you're on your own.
You should know the terminology.
Yes, so you do need to know the terminology. Okay. And the final way is the easiest way. It's called noble gas notation. When we were doing those, you probably were getting frustrated because you always had to start up here. It was always 1s2, 2s2, 2p6, right? The noble gas notation gets rid of that. It says, well, if I'm giving you directions from here to a store in Ocala, I don't need to tell you, well, get on I-75 and drive so many miles. You know how to get to Ocala. So I can tell you, go to Ocala and then get off on this exit and then do this, this, and this. So what this does is it starts at a noble gas and then you write everything after that. So if we were doing sodium, if you were doing electron configuration, you would write out 1s2, 2s2, 2p6. But all of that is the electron configuration for neon. So I can just say, start at neon, and then go 3s1. And then you're done. And the way we do that is we write a noble gas in brackets, and then we write everything after. So what this is showing is this is iron and argon. This is iron, this is argon. all of this is the same for both of them. And so you can, for iron, you can just say, start at argon, and then write what's left. And so in this case, we basically erased that and copied that down here. But if we were starting from scratch, we could say iron. We've got iron right here. Let's go backwards to find the last noble gas we passed, which is argon. So I put argon in brackets, and then I start here. 4s2, 3d6. Done. So for magnesium, it would be neon, 3s2. Done. Does that make sense? Let's use it. I guess there's no examples. So somebody pick an element. Any element that is not in the F's down at the bottom. Silicone? Silicon. Silicon number 14. Silicone and silicon are actually different. This is silicon, this is number 14. So I'm going to write silicon. What is the noble gas just before silicon?
Neon.
Neon. So I write neon. And now I am starting here. So what comes after that?
3s2.
3s2. Then what? 3p2.
P2.
I'm done. So if you can do electron configuration, you can do this. So if you can do orbital diagrams, you can do electron configurations. If you can do electron configurations, you can do this. In all the cases, there are ways to just from scratch go straight to this. But if you have to, you can do the orbital diagram with the boxes, convert that into an electron configuration, and then convert that into this. So like he was asking before, on an exam, if I want this, I would probably bold, highlight, and bold, underline, and italicize that I want noble gas notation, and then I would probably give you an example of what noble gas notation looks like.
Wait, can you do why you started at 3s2 again?
So we were going, what were we going?
Silicon.
Silicon.
Oh.
So we were going here, and so we went backwards to the last noble gas.
You can't go forward to argon.
Right.
Yeah.
You have to go backwards to neon, so then we started at neon. So then we just write the electron configuration for everything after neon, which starts here. So this is 3s2, 3p2. So if we were doing selenium, what noble gas would we use?
Argon.
We would use argon. We would go backwards to argon. So we would do argon, 4s2, 3d10, and then 4p, 1, 2, 3, 4. Okay? Okay. So a while ago, when we first started about ions, I used the word valence electrons. I didn't even tell you what they were. Did anybody know what they were? Outer shell. Very good. Why are you in this class? Anatomy. Good answer. So valence electrons are what they said, the outer shell. Okay? A noble gas has a full outer shell. And every element wants to be like a noble gas. If you just have a couple elements in your outer shell, it's easiest to just get rid of them and fall back to the shell that's inside that's already full. If your outer shell is almost full, it's easier to just grab an extra one or two so that it's full. So if you want to count the number of valence electrons in an element, and let's say we have an electron configuration, in this case, it's noble gas notation. You're gonna, well, let me do it here. Let's say we got, let's do our germanium. that's the noble gas notation for germanium.
So is 2, 10, 2, are those your valence electrons?
So if you're looking at this, the valence electrons are only the ones in orbitals that have the highest number. So if you have 4s2, 3d10, 4p2, you have 4, 3, 4. You only count the ones that are in the 4s. Okay? You skip the 3s. You can have no more than 8 valence electrons. Because you skip the d's, that means you only count s's and p's. S's have 2, p's have 6. So together, you have 8. That's why there are 8 valence electron maximum, because you skip the d's. The reason you skip the d's, this is more complicated than you need to worry about, but if it helps you to understand, essentially what happens is when you get a new electron, it goes the easiest place. And it is easier for an electron to go into the 4s orbital than it is for it to go into the 3d's. But it's easier to go into the 3d's than the 4p's. So it fills the 4s, then goes back to the 3d, and then goes forward to the 4p. But what that's telling us is because you went backwards to 3, you're essentially stuffing more electrons into the middle of the cloud. You're not adding any extra to the outer shell. You're just sticking them into the middle. And so you're not adding valence electrons. So we have 2 here and 2 there. Germanium has 4 valence electrons. The easier, go ahead.
You don't count the ones that are within argon?
No, because argon, everything here, there's 3s, 2s, and 1s. The 4 is higher.
So you only count the 4s?
You only count the highest number. And the highest number is 4.
Okay.
The easier way to do it is we can just look at the periodic table again. Because we skipped the d's, there's 1 valence electron, 2, 3, 4, 5, 6, 7, 8. So I can just ask, how many valence electrons are in indium? 1, 2, 3. Done. Tin has 4. Iodine has 7. Oxygen has 6. 1, 2, 3, 4, 5, 6, 7, 8. And so now looking backwards to when we were making ions, it probably makes a little bit more sense. How many valence electrons does sodium have? 1. It has 1 extra orbital on the outside, just has a single electron in it. If it can kick that away, it gets rid of that whole outer shell and exposes the one underneath that has 8. Chlorine has 7. It wants 8. If it can just pick up 1 extra, its outer shell is now full. So it forms a negative charge because it gained 1. And now what we'll see, I think next week, is why sodium makes a compound with chlorine. Sodium wants to lose 1. Chlorine wants to gain 1. So if sodium gives 1 to chlorine, everybody's happy.
So if you have, we're trying to find the valence electrons in the D group, would you have to do like this entire?
In the D, it's very simple.
Oh.
Because the number for the D is always going to be lower than the number for the S's. The S's are always going to win out. And so everything in the D group has 2.
Oh.
And so essentially you've got 1, 2, 2, 3, 4, 5, 6, 7, 8. So cobalt has 2. Manganese has 2. Molybdenum has 2. Yes. Yes. That's why they all form +2 charge, because they have 2 valence electrons that they want to get rid of. And so this is electron configuration completely written out. So we pick the highest number, the 4. So we ignore the 1s, the 2s, and 3s. There's 4, so there's 2 and 5, so there's 7 valence electrons. And that was bromine, but you can just look at bromine and say it's in that group, so it has 7. Everybody okay with counting 1, 2, 2, 3, 4, 5, 6, 7, 8? Then we won't do all of this. You can do electron configuration for ions also. My suggestion is to do the electron configuration for the atom. Just say you want to do a sodium ion, do it for the atom like you would always do it, and then subtract 1. Just erase the last electron. For chlorine, do it just for chlorine like we would have done anyways, and add 1 extra at the end. That's the easiest way to do that. If you do it, electron configuration for sodium, we had 1s2, 2s2, 2p6, 3s1. You erase that 1 off the 3s, the whole thing goes away, and now you just have that. The 3s1 needs to be right there. Okay. How many slides do we have left? 9?
8.
Okay. 9, 8, 7. Do I hear 6?
8. There's 67 slides and we have 59. We're on 59.
So these are Lewis symbols. Okay? This is different than a Lewis dot structure. If Lewis dot structure immediately makes your stomach shrivel up in your chest, don't worry, you got a few more weeks. These are Lewis symbols. Okay? These are much, much easier. Lewis symbol is just literally drawing a dot for every valence electron an atom has. So if I say, I want to write the Lewis symbol for calcium. Calcium is here. How many valence electrons does it have? 2. So I'm going to write calcium, and then I have to put 2 dots around it to represent the 2 valence electrons. But remember that electrons are antisocial. They're not going to pair unless they have to, and they're going to stay as far away from each other as possible. So I'm going to put number 1 here, and the second one's going to go opposite. That is the Lewis symbol for calcium. Okay? Because you can have up to 8 valence electrons, let's do argon. Argon is a noble gas. It has 8. But I write that, I'm going to have 8 dots. Okay? I learned that you had to draw the dots in a specific order. I'm not going to make you do it in a specific order. I just don't want you to pair them unless you have to. And when you do the first 2, put them opposite of each other.
Wait, don't we have to share with each other?
Eventually, we'll get there. And so I'm going to put the first one here. That's 1, 2, 3, 4. I've got my 4. Now the 5th one's going to have to make a pair. So I'm going to come back and do 5, 6, 7, 8. And so chlorine has 7. So I would do 1, 2, 3, 4, 5, 6, 7. More or less, if you can make 1 dot for each valence electron, you're halfway there. Don't pair them unless you have to. And then put the first 2 opposite of each other.
So the last spot to get filled is the bottom?
In the order that I do it, but you don't have to do it in my order. If you want to put the first one on top and the second one on the bottom, that's fine. It's just when I learned it was left, right, up, down. And it's stuck in my head since then. Okay. So, we said it's the periodic table of the elements. And we said that the properties change as we go from left to right. And the pattern is generally the same no matter what row or period you are in. And so we have what we call periodic properties. In general, as you go from left to right, we get changes in reactivity, ionization energy, which means how easily something loses electrons, and the size of our atoms. We're going to talk about the trends in each of them. So this is the alkali metals in water. I said generally as you go down they get more reactive. This is, you're actually seeing lithium, sodium, potassium, rubidium, cesium, and when they put the francium in, it killed the cameraman. So francium isn't there. But you can see very clearly that it's getting more reactive, right? It doesn't matter which group you are in. As you go from the top to the bottom, things get more reactive. Ionization energy. To me, the term ionization energy is a little misleading. To me, what that sounds like is the energy needed to make it an ion. Not even taking into consideration whether it's a positive or a negative ion. What it actually is the energy required to remove a valence electron. So what it basically is the energy needed to make something into a positive ion. Whether it wants to or not, it always deals with making a positive ion. So the elements on the left-hand side, do they want to become positive or negative? They're metals. Positive. Metals make positive ions. And so if they want to make positive ions, does that mean they want to gain or lose electrons? Lose. So things over here want to lose electrons. If I have something that I don't like, you're not going to have to pay me much to make me get rid of it. And so the ionization energy for things on the left side are very low. Chlorine, fluorine, how many valence electrons do they have? 7. They're 1 away from a full valence electron orbital.
This close to being a noble gas.
They're that close to being a noble gas. And so, do they want to gain or lose electrons? They want to gain. And so you're going to have to put a lot of energy into them to make them lose 1. Because if they lose 1, they're not 2 away from being full. So you're going to have to really pay them a lot of energy to get them to get rid of it. And so what this shows us is we go from left to right. Ionization energy goes up. That is our first trend. As you go from left to right, ionization energy goes up. Magnesium, when it loses the first electron, gives off some energy. Magnesium is here. So sodium loses its first electron, it's not going to lose as much. Okay? Don't worry too much about that formula. This is just saying magnesium makes a magnesium ion with a +1 charge, giving off 1 electron. Ionization energy always deals with the first electron. Yes, magnesium wants to lose 2, but this measurement only deals with the first one. So we said if you go from left to right, ionization energy gets larger. So in this we should say it increases from left to right. We talked about why, and that makes sense. At least to me it makes sense. If I want 8 and I already have 7, it's tough to get me to give 1 up. It doesn't make quite as much sense as the trend going vertically. As you go from the bottom to the top, ionization energy gets larger. Okay? The reason that is if you look at these 2 atoms, okay? As you go from the top to the bottom, you have to continually add more orbitals as they get full. And so, if you're dealing with something at the bottom, you're on an orbital that is way out here. What holds an electron in an atom, prevents it from flying away, is the fact that it's negatively charged, and the nucleus in the middle is positively charged. So there's an attraction there. But if the electron is a long way from the nucleus, that attraction isn't as strong. So it's easier to grab it and pluck it off. So the things at the top are stronger because they have a higher ionization energy because the attraction is stronger, so when you grab it, you have to pull harder to get it off. If it's way out here, it barely even knows the nucleus exists, and so you say, hey, want to go someplace? He'll say, okay.
So it's like the less orbitals, the big, like the farther
the higher the number. So 1, 2, 3, 4, 5, 6, 7.
Yeah, and you're saying it's because like, is it because there's more orbitals? Than
Right, and so as you add them, you have to get bigger and bigger. And so there are two ways to remember. You can either remember the individual trends, most like possibly using the reasoning behind them, or you can just remember which corner is the highest. Which corner is the highest? Top right. So if you can remember that helium has the highest ionization energy, that tells you everything you need to know. Because helium is the highest, that means the right side must be the highest. That also must mean that the top is the highest. Or if you want to remember which one is the smallest, you can do that also. Francium is the smallest. If you remember that one thing, that will tell you everything.
Even though it's the most reactive.
Yes. So, if I ask you which has the greater ionization energy, magnesium or calcium, what would you tell me? Magnesium because it's higher. Oxygen or fluorine? Fluorine because it's further to the right. Sulfur or fluorine? Fluorine. It is further right and higher.
You have these questions all the time.
There will be some. Atomic radius is very similar, but the pattern is opposite. The largest radius, the radius is think of the distance from the nucleus to the outermost electron. So the nucleus to the electron is also the same number as if you had two atoms next to each other, the distance between the two nuclei. But I would just imagine in your mind, one single atom is the distance from the center to the outside. And so a larger radius means a larger atom. The largest one is francium in the bottom left. And it makes sense going from top to bottom, because as we said, when you go from top to bottom, you have to add more and more shells. And when you add a shell, it goes on the outside. And so your atom gets larger. That one makes sense. What seems a little bit opposite, at least to me, is when you add electrons going from left to right, it actually shrinks. Magnesium has one more electron than sodium. It would seem, if you add an electron, it's going to get bigger. It actually shrinks. And that's because, remember, what's holding things in place is the attraction between positive and negative. When you add that second electron to 2s, it goes in s. S is as big as it's going to be, and it's not going to get bigger when you add another one in. It's like when you put something in the trunk of your car, the trunk doesn't get bigger, right? So you add another electron, so s doesn't get bigger, but now you have a stronger attraction between the positive in the center and the negative on the outside. There's now more negative charge on the outside. So the attraction gets a little bit stronger, and so the s gets pulled in just a little bit closer. And so it shrinks as you go from left to right. And so the biggest one is francium. Francium has the smallest ionization energy and the largest radius. Helium has the highest ionization energy and the smallest radius. So if you can remember one of them, and then remember that the other one is opposite, you've got the whole thing memorized. So this is just showing changes in size. So helium is the smallest, francium is the largest.
Well, hydrogen is pretty tiny too.
Yes. So what is larger, magnesium or calcium? Calcium because it's lower. Oxygen or fluorine? Oxygen because it's further left. And then sulfur or fluorine? Sulfur because it is furthest left and lowest. That's the last one?
Yes.
Okay. Questions about this? Yes. Next week, please. Next week. Other questions? Okay. Then we will go over the Canvas homework from last week. remember that the scientific method post-lab, the one from 2 weeks ago that a lot of you already turned in, is due today. The post-lab from last week's lab that we skipped, you still have to do it. It is due this Thursday. There are no questions on there that relate to the actual lab. So there's nothing stopping us from doing it. So make sure you have that on Thursday.
What was due today?
The scientific method post-lab. It's possible you already did it. If you're not sure, I can check when you finish the quiz. A lot of you did it right after you finished the lab. Or you would like. So number one here wants us to take that number, 73,937, put it into scientific notation. How do we do that?
Move the decimal.
Decimal.